Okay, gases are very different, very different than liquids and solids. Mainly because the distance between the atoms or molecules is very far apart relative to liquids and solids, big time far apart. So they're compressible. That's where we got the 22.4 liters per mole at standard temperature and pressure. Now, if it's not at standard temperature and pressure, what do we do then? Okay, so instead of this would be STP, and that can be in different units too. It can be in joule, for example, and if we're talking about pressure, different units. Now, what relates that is this equation. The ideal gas law. Now, the ideal gas law works when we have relatively low pressures, not 300 atmospheres. When we have relatively reasonable temperatures, not, million degrees, then there's deviations from the ideal gas law. But under normal circumstances, this works fine. PV is equal to nRT. So if we put in, now this P stands for pressure, obviously, V is volume in liters, N is moles, R is a universal gas constant, and that varies depending on what units we're using. And then T is temperature in Kelvin. Kelvin. All right, so when we're doing stoichiometry, the first step is to convert to moles. When working with gases, non-ideal gases, we've got to use that for the first step of stoichiometry. Now, we're not going to do gas stoichiometry here except for ideal gas laws, but this is what we'd have to use in a stoichiometry problem if it was non-ideal. And you'll get to this a lot in 1A and possibly 2A, depending on who you get. Now, one teacher told me, I was talking to her about this, and she says, well, I never use ideal 22.4. She said, that's totally unrealistic. I always use non-ideal conditions. Well, it really complicates stoichiometry if you use non-ideal. And to me, it fuzzies up the concept of doing stoichiometry. So that's why in this class I use 22.4 all the time. Okay, so let's talk about R for a second here. Basically, we've got, when you look at the units here, we've got degrees K, we've got atmospheres, and we've got liters. So the R value when we're using Kelvin, atmospheres, and liters is 0812. Yeah. It's a constant that links all the pressure, volume, temperature together in moles. R. That's the abbreviation. Okay, so and that cancels out all the units, so it makes sense. Otherwise, it'd be weird. Okay, so how many variables have we got there? Well, we've got 4 variables. So whenever you're doing a gas problem, I have to supply you with 3 of those 4. Otherwise, you can't do the problem. Now, on Monday, Tuesday, we're going to be having a whole bunch of stations set up where you're going to be testing this. And they're really kind of cool. They're hands-on. They're real quick to do. I'll do some demos with some cans and showing the pressure of what the air weighs. Yeah.
Just noticing you said have 2 things there.
PV equals nRT, and then N equals RT over PV. Shouldn't it be PV over RT? RT, right. Yeah. Okay, well, let's say we were looking at a situation. So what's the volume of hydrogen gas at 34 degrees C, 2.3 atmospheres? So we want volumes. We're going to solve for V. So V is equal to nRT over P. So R is always going to be 0812. And we're not changing the number of moles. We're going to assume it's 1 mole of gas. Now I gave you 34 degrees Celsius. It needs to be in kelvins. We're going to add 273 to that. Okay, so that's going to be the volume. Just a very simple substitution. Now, there's two situations. One is you're going to have non-ideal conditions and you're asked for the pressure, temperature, or volume. Usually it's volume, by the way, 9 times out of 10. But other gas problems, we have changes. For example, if we have a balloon, and we put the balloon in the bottom of a swimming pool. What does the balloon do? Does it change size? I have a no. I have a yes. Got to be one of the two. Okay, it's going to get smaller because the pressure of the water is going to compress it. So the volume is going down, so the pressure inside is going to go up. Temperature could change also. There's a lot of variables. So the two types of gas problems are going to be what's the missing variable, volume, temperature, pressure, or we have changing conditions. Now, most of the little parts of the lab on Monday, Tuesday are changing conditions. We'll make the volume smaller. So what's the pressure do? It's going to go up. One thing about these relationships, if P goes up and N, R, T are constant, what must volume do? Okay, so volume must go down to maintain the constant nRT. So pressure volume are indirectly related. Volume goes up, pressure's got to go down. So this is an indirect relationship. Okay, let's look at PT. If pressure goes up, what must temperature do? Goes up. Pressure goes up, N goes up also. So everything is in direct relation except PV. They're indirectly related. Now, the way you'll see indirect relationships, so these are direct. This is the way you write indirect relationships. P is indirectly related to the inverse of volume. And a direct relationship is like this. P goes up, T goes up. E goes down, pressure goes down. So PT, we take a balloon up to Mount Everest. What does the balloon do? Okay, is it cold or hot at Mount Everest? So what does the balloon do? Yeah, the pressure inside gets smaller, so the balloon gets smaller. No, the opposite, it gets smaller.
So then why would you drive to, let's say, like Tahoe and have like back chips in the back chips box?
What about that?
But just like Mount Everest, the elevation is higher. Then Tahoe is cold too, not as cold as Mount Everest, but.
Well, you have two things going on. Okay, let's go to the bag of chips. Okay, the bag of chips gets big. Okay, is anything can go in or out of the bag of chips? Gas wise, because it's sealed, right? If it wasn't sealed, what would the bag of chips do? Probably nothing, right?
But technically a balloon is sealed as well,
Right.
so why does the bag of chips pop open, even though it's sealed? And the balloon doesn't pop.
Right. When you're going up to Tahoe in the winter, what does the bag of chips do?
Yeah.
In your nice warm car. What about if you're outside?
In the car.
Car will pop outside, it will not pop though. Because you have two overriding things. You have temperature and you have pressure. Pressure goes down. Temperature goes down. So. Yeah,
For the Everest example, pressure would also be going down though, right? It's not enough to counteract the temperature change.
they're both extreme at Mount Everest. It gets really cold and it gets, pressure goes way down. Everest is what, like 17,000 feet, something like that?
No, it's like 35,000 feet.
Oh, Mount Whitney's 17,000. Yeah,
Everest,
really high, anyway. You don't have to look it up. I believe you. 35 is fine. So anyway, we have changing conditions. 29,000. Gnarly high, yes. All right, so let's look at some conditions here. Okay, we have, initial and final conditions. And we're using PV is equal to nRT initial, PV is equal to nRT final. Okay, what's the same on both those conditions? Does R change? No. R does not change. Does P change? V change, T change, all three of those change. But R is a constant by definition, does not change. So if we solve for R, now we can set these equal. So we have the initial pressure, volume, okay, does everyone see why we can set those equal? Initial final conditions of EV over NT. So now if we have an initial pressure and it changes and these others remain constant, then we know what's going on. If nothing comes in or out of the enclosure, then N is going to remain the same. Temperature could remain the same if you maintained it. So let's look at a problem where the conditions change. Okay, a solid balloon, in other words, not an expandable balloon. Yeah. A C next to the what? Okay, so we have a solid balloon, meaning it's not a balloon that it can expand or contract. It's solid. Okay, and it's at 34 degrees, 2.3 atmospheres. We heat that to 66 degrees. What's the final temperature? So we're using this up here. And because it's solid and sealed, can anything come in or leave? No. So that means moles are equal. So those cancel. All right. What about so that means we're working with PV. Okay, the initial conditions for pressure is 2.3. The volume. Why didn't I specify the volume? And the temperature is, we don't know what the initial temperature is. Oh, we do. I'm sorry. Let me back up. We don't know the final temperature. So 34, it was 307 Kelvin. Pressure. What's the final pressure? Now, if you don't specify a pressure changing, assume it's constant. Okay? So that means the P's cancel. Those are constant. Okay, so the liters, because it's solid, does it change? No, it remains 5, 6 also. We don't know the final temperature. Now, those cancel. Those cancel. Does everyone see how they cancel? If you divide both sides by one of those, they both cancel out. So if you have something on both sides of the equation, like what does that simplify to? X equals Y because the sevens cancel. So like within this case, the volume cancels and the atmospheric pressure cancels. Anything that's going to change is the temperature. So we solve for T final temperature. Now notice the final temperature is on the denominator side on the bottom. So the easiest way to solve this is to cross multiply. Whenever we bring something across the equal sign, it changes in terms of the fraction. If it's on the bottom, it goes to the top. If it's on the top, it goes to the bottom. So if we were to bring this over here, now it's on the top. If we bring this over here, it's now on the top. So what's the final temperature?
So
No change.
what's the 66 for? The original problem. Oh, I get
Actually, that's a silly problem, isn't it? I told you the two temperatures and I asked you for the final one. The answer is 66. Let me, no, just let me. That's right. What is this? Um, let's look at the final pressure. Okay. On a test, that would be a trick question, and remember, I don't do trick questions. Okay, so we've got we don't know the final. Okay, so we don't know the final pressure. We know the initial pressure. The initial pressure is 2.3. The volume, because it's solid, does not change. Temperature is initial, this is initial conditions, final conditions. The initial temperature is 307 Kelvin. Final temperature is Okay, so just offhand, what do you think the pressure is gonna do? Stay the same? What is it gonna do? Gonna go up because remember, pressure is directly proportional to temperature. So when you're all said and done, make sure your number is higher than what you started with. Just to validate your answer. Okay, so we're gonna solve for P sub F. That means we're gonna cross multiply here, cross multiply here. Okay, so we've got, and then 5.6 is on both sides, so we can cancel that. So we're gonna end up with 2.3 atmospheres, 339 K, all over 307 K, and that's equal to P sub F.
You would add.
Hmm. And we convert to Celsius to Kelvin. Okay, does everyone see where I got these guys? Now look at the units. The K's cancel, leaves us with atmospheres. What are we trying to calculate? Atmospheres. So the units work out. Then we just grind out the number. So remember, we expect the pressure to go up because of PT is direct. And lo and behold, it does go up. Now, interestingly, it doesn't go up a lot. The reason why it doesn't go up a lot is because we started with 33 degrees Celsius, went to 66. That's doubling, right? So would you expect the pressure to double? Why?
Given Celsius, but it's actually Kelvin that we're looking at. Kelvin is 200 and something higher than Celsius, therefore, even though it's doubling in Celsius, it's only a change of about 10% in Kelvin.
Exactly. Because Kelvin, the numbers are much bigger. The change is much smaller. So that ratio is smaller. So it doesn't go up as much as you'd think if we're just looking at Celsius. So if we're just looking at Celsius, gosh, it'd be double. Don't even have to calculate anything, right? But in Kelvin. So you'd have to double the Kelvin to double the pressure. And you're starting off at 303, so you'd have to have 606 Kelvin. And that's like 400 and something degrees Celsius. So it's crucial that you convert to Kelvin. Now, this is the essence of gas problems. We have two kinds of problems. We have PV is equal to RT. You're given parameters and ask what the volume is or the temperature, whatever. And then the other type problem is we change conditions. Like the problem after I modified it. So it's not a trick problem. Okay, does this make sense? Now, it's important for you to be comfortable with this manipulation. So on a test, if you set this up like that, but you got the wrong answer, the setup is correct. I would just mark off because you didn't get the right numerical answer. The setup is correct though. Okay. Mhm.
Five.
Yep. Sig fig wise, 2 sig figs, 2 sig figs, 3 sig figs, 3 sig figs, 2 sig figs. So yes, 2 sig figs. And like always, sig figs rule. Yeah. Okay, is everyone comfortable with these? Let's do another one. Okay, a solid balloon. That means solid, it's not gonna change volume. I still specified it, but it's not gonna change. It's gonna go from 5.6 initially to 5.6 final. It's compressed to 2 liters. So we're taking that 5.6 now and crushing it down to 2. And we're gonna reduce the temperature from 34 degrees down to 10 degrees Celsius. If we measure the pressure initially inside the solid balloon, it is 1.2 atmosphere. What's the final pressure? So okay, so N's constant. We're not adding gas or taking gas out. Okay. So the initial pressure is 1.2 atmospheres. And the volume is 5.6. And the initial volume, pressure, temperature is 34. That would be 307 again. Final pressure, we don't know. Volume is 2 liters. And the temperature is 283 K. So we've got 8 variables. 8 variables. Now, some of them are the same initial final conditions, they go away. You can cancel them out. But if they do change, you have to leave them in. Okay, so let's solve for P, final pressure. So we're going to cross multiply. So this goes over here. This goes down here. Cross multiplying, just like algebra. We have 1.2 atmospheres, 5.6 liters, 307 K. and 2.0 loops. So again, when you cross multiply, if it's on the bottom, it goes to the top. If it's on the top, it goes to the bottom. And the other way to do it is you multiply or divide each side by the same thing so it cancels out. That's the classic way in beginning algebra. In some algebra classes, they teach you cross multiplying and some don't. When I taught algebra in high school, I taught cross multiplying. So it never fails. Okay, does everyone see where I got all the p-values? So pressure goes from 2 to 3.1. Now you have two things that are kind of counteracting. The temperature is going down, so that means the pressure is going to go down. But also the volume goes down, which makes the pressure go up. So you have two competing things. One makes it go up, the other makes it go down. So there's no way for you to actually guess which it should be your answer. Now you can look at the magnitude change of the volume. The volume changes by more than half. So that means intuitively, indirectly, that means it should double. Now the pressure or the temperature goes from 307 to 283, which is not a lot change temperature wise. Okay. All right, so those are the type problems you're going to see on Monday, Tuesday. You're not going to be doing numbers though. You're going to be just kind of having a feel for it. And for next week, this is what you're going to be dealing with. These here. For the lab. Okay, that's what I wanted to cover today on gases. Short but sweet. Okay, are there any questions about the algebra part of this? Cross multiplying or anything like that? You've got to know how to do that, otherwise this problem you can't work it. Okay.